Good afternoon. First of all, all what I lectured on up to now can be found in two classical textbooks. First one is by Andri and Silverman, which is title is Lafontaine Geometry, or maybe an introduction to Lafontaine geometry, or in the one by Bombieri and Gubler, which is heights in Lafontaine geometry. The first is by Springer Verlag and second by Cambridge University Press. I promised some notes of mine, but there will be no complete proofs, while in these books you find all proofs. Today I'd like to give a proof of Siegel theorem using the subspace theorem. First, I'd like to tell some preliminaries from the algebraic geometry of curves, so especially about divisors and linear systems. Curves. So suppose C tilde as usually I use a tilde for a complete curve. So it's a smooth projective curve. A divisor C tilde is a formal linear combination of points of C tilde. So divisor D will be an expression like A1 Q1 plus AR QR, where the AI are integers and the QI are points of the curve. The degree of the divisor is the sum of the coefficients. For a rational function phi, C tilde K is the field where it is defined. The divisor of phi is the sum with multiplicities over its zeros and poles. So multiplicity is positive in the case of zeros and negative in the case of poles. Given a divisor D, the vector space L of D is also called the linear system associated with D, is the set of function f. Uh, Actually, here I should eliminate the 0 function, such that the divisor phi plus d is positive, and now I add 0. And I forgot to say that the divisor is positive. It means that all its coefficients are non-negative. So d at least 0, where d is this one, means that ai is 0 for every I. Okay, so this is a vector space. It is always of finite dimension, and what I need is a weak version of the Riemann-Roch theorem, giving a formula for the dimension of this linear space. Actually, I call it asymptotic Riemann-Roch theorem. It's that for the positive, we have that L of n times d, the dimension of L and d, is at least the n times degree of d plus big O of 1. And actually, a more precise form L and D is at least n degree of d plus 1 minus g, where g is the genus tilde, and equality holds for large n. If you have never seen this, the Riemann-Roch theorem, or not even its weak form, well, it's not a problem. It's not a big problem. In every particular, in every concrete case, this theorem can be proved just by using classical linear algebra. I will show how. First, the most elementary example. First example, take C tilde to be P1 and D to be the single point at infinity. So in this case, L of ND is the set of rational functions having no poles, but possibly at infinity, and at infinity they have a pole of degree at most n. So if a rational function having no pole, but at infinity, is a polynomial, and a polynomial with a pole at infinity of degree at most n is a polynomial of degree at most n. And well, they are generated by constant one function, the monomial x, and so on up to x to the n. So there are n plus 1 elements, so you obtain n times the degree of D, which is 1, plus 1 minus 0, since the genus of P1 is 0. And so you have the exact formula with no exception. Let us consider a second example. Which is the example which will be useful for us. Take an affine curve C. So, well, consider this particular case. C is an affine plane curve. And C tilde is a completion of C in P2, and we suppose that C is defined by an equation f of x y equals 0 of degree r, and to simplify, we suppose monic in one variable, for instance in epsilon. And suppose that C tilde minus C, so the set of points at infinity, consists of r distinct points, as many points as the degree of f. This will be the case for a generic equation in A2. So now if we consider the set of rational function on the complete curve C tilde, whose poles are only at the points Q1, QR, then we obtain the regular function on C. And by Hilbert and Nullstellensatz, the regular functions of on C are the regular functions on the plane, so the polynomial in two variables, restricted to the curve C. So they form the quotient of the ring of polynomials modulo the ideal generated by F. So this is also the union for all n of L and D. And now, what about a single element L and D? The functions which are regular on C and at infinity have poles of order at most n are induced by polynomials in x, y of degree at most n. Pardon? Yes, sorry. D is the sum of course. D is Q1 plus QR. Okay. And these are so restrictions to C of polynomials of degree at most n, polynomials in x, y. Now, since fxy supposed to be of the form y to the r minus plus a1 of x y r minus 1 plus so on, you have that y to the r is congruent to a polynomial of degree less than or equal to r minus 1 modulo the equation of the curve. So every polynomial can be rewritten as a polynomial in xy of degree at most r minus 1 in y, which will induce the same function on C. So every polynomial in xy is congruent to a polynomial of degree at most r minus 1 in y. So the polynomial of degree most n can have a representative of the form y r minus 1 b1 of x plus y r minus 2 b2 of x plus br of x, where the degree of b I x is at most n minus how it is r plus 1 minus I think. Let's see, for I equal r, no, there is no plus 1. Okay. Plus I. Okay. So the dimension of this space of polynomial for each I there is n minus r plus I plus 1 possibility for its coefficients. So the total dimension is the sum of I to 1 to r is n minus r plus I plus 1. So you obtain n times r minus sum of I from 1 to r of r minus I and then plus r. Okay, and so this is n times the degree of D, and this is a constant. It's independent on n, and actually it turns out it is 1 minus g, where g by this by the genus formula is r minus 1, r minus 2 over 2. Anyway, if you take this as a definition of G, this is an identity. So this is Riemann-Roch theorem in the case we need at least, well, for a fine plane curve and for an affine curve on an affine space of higher dimension, the procedure is exactly the same. It's just a simple exercise in linear algebra. Now, for starting the proof of Siegel theorem, I'd like to come back to the proof of two theorem. So remark the proof So we had a curve, an affine curve of equation f of x, y equals constant, and f x, y was x minus alpha 1 y, x minus alpha r y. Now I use r for the degree. So you can see its completion as C plus the points at infinity, and Qi is the points alpha I and 0. And in the proof, we use the functions. The main point is that the function x minus alpha 1, one of the alpha, for instance, alpha 1 y, is as a high 0 at Q1. And then this function and any other linear function in x, y, or the one constant. So this is, let's call it f1. You take f2, any linear function in 1 x, y independent of f1, and pardon? This function, we saw last time that it vanishes at the point alpha 1, 1, 0, and it has poles in the other. Okay. So this was the main point for the Diophantine part of the proof to work. And we used the two linear functions in 1x, y, one of which had to be carefully chosen, and the second one was not important, to obtain a morphism from C tilde to P1, given by P sent to F1P, F2P. And then we applied the Roth theorem, so basically the Diophantine approximation statement of P1. So, in geometric terms, we had the divisor D, which was Q1 plus QR. This divisor has at least 3 independent sections, 1 x, y, but we just need to take 2 of them, x minus alpha 1 y and a second one, and working with these 2 functions we obtained we obtain what we wanted after application of a Roth theorem. The new idea is that for an arbitrary curve, not so particular as a two-way curve, we have to work more generally with L of ND instead of just L of D, and consider not only two but many, for instance, as many as possible sections, so functions here, and consider complete linear system so a basis of the whole vector space. And we construct in this way morphism from C tilde to a vector space Pm, and then apply the Fountain approximation in Pm instead of P1. So instead of Roth theorem, we had to apply the subspace theorem. Now, let's begin the proof. First, I recall the statement. And actually, we start with a particular case, theorem Siegel, first version, which will imply the general version, as I will show later, using a Chevalier-Weil theorem, so not using anything of Diophantine approximation again. So the first version says the following: if so let K be a number field, so OS a ring of S integers, as usual, S is a finite set of places of K containing the Archimedean ones. I don't write it again. So C is fine, smooth curve. C tilde is its completion, and we suppose that C tilde minus C has at least 3 points. And then C of OS is finite. So there are only finitely many points on S integral points on C. So as I said, this is one of the cases where Siegel proved the finiteness. The other case is when the genus of C is non-zero and there is at least 1 point at infinity. But this second case can be reduced to this one. So this is the crucial case where the Diophantine approximation has to be used. So proof. First of all, we enlarge K so that the points at infinity are all defined over K. So the points at infinity are the points Q1, QR, Qi is a rational point, and R is at least 3. So we consider linear system L of n Q1 plus QR, and its dimension is dn, or sometimes I will write just d, omitting n, and it will be at least n r plus a constant, and by the way, we know the constant is 1 minus g, but anyway, we just need that there is a constant here, and we just need this for large n. Then we can view C, which is, as I said, C tilde minus the points at infinity, as a closed subset of a certain affine space. So the regular function on C can be written as polynomial functions in m variable for a certain m, and in particular the elements of this linear system can be viewed as a polynomial in m variables restricted to the curve. Now consider phi 1, phi d be any basis of L of n d. Now I can suppose that they are polynomials in the indeterminates x1, xm with s-integral coefficients. Otherwise, I multiply all of them by a constant. So we can suppose that for every point P in C of OS, so for every integral point, the phi I of P is an s-integral for I from 1 to d. Now we're supposed to have an infinite sequence of integral points. I suppose that Pn is infinite in COS. Now, for each nu in S, we have the set C tilde of points with coordinate in the completion of K at the place nu. Well, this is a compact set because C tilde is projective and K nu is a complete field. Compact. So from the sequence we can extract an infinite subsequence which converges, and we can do it for every nu. So for the first nu we extract an infinite subsequence, then we consider this subsequence for the second nu, and if it does not converge we extract again, and so finally we can suppose that for every nu, since this set S is finite, the n converges to a certain point, the nu of the complete curve over the complete field. And this point may be one of the points at infinity, or maybe a point at the finite part of the curve. So we let S prime be the set of nu in S such that P sub nu is one of the points at infinity. And S second, its complement. Now we want to construct for each nu in S a basis of L and D which will be suitable for our purposes. So for nu in S second, just choose any basis, for instance the one already choose phi 1 phi d. The contrary for nu in S prime. Here we try to have functions having zeros of order as high as possible at the target point P nu. So the functions in this vector space will have at most at worst they will have a pole of order n at the point P nu. So first the first element of the basis is chosen to have a maximal pole. Then I claim that I can choose a second element in the basis, which will be necessarily independent of the first one, which has a pole of lower order, because the vector space the subvector space of functions having a pole of order less than n minus 1 is a hyperplane in L n Q1 plus QR. Simply, every function here can be developed in as a Laurent series around the point P nu. You just look at the coefficient of exponent minus n, giving the pole of order n. The subset in which this coefficient vanishes is a subset defined by a single linear equation. So it will be a hyperplane. So I choose in this hyperplane the second element of the basis. So the first element, call it phi 1, and choose phi nu 2 in this hyperplane. Then all the Laurent developments of the functions in this hyperplane will omit the term with exponents minus n. So they will start with minus n plus 1, or possibly for some reason it might happen that automatically there will be a lower pole. But certainly the function which gives the coefficient of exponents minus n plus 1 is a linear function in this hyperplane. So if it is identically 0, it's okay, otherwise its kernel will be a hyperplane. So those functions with a pole of order at most n minus 2 either form a hyperplane of this hyperplane, or they form the hyperplane altogether. So in any case, I can choose phi nu 3 such that its pole is at most n minus 2. And so I can go on, and for every I from 1 to d, choose phi nu I, so that its pole as order most n minus I plus 1. By this we mean when the right hand term is negative, that it must have a 0. So a pole of order at most minus 1 for me it means a 0. Starting from from I larger than n, I shall begin to require zeros. And so the first element have poles of decreasing order, and starting at a certain point I will have zeros. And then we can write each phi nu I as a linear form L nu I in phi 1 phi d. So I consider phi 1 phi d as the variables, and these new functions are linear forms in the variables. Since I've written the subspace theorem in terms of linear forms. Yes, yes. Everything here is defined over K. But things I suppose that the points are defined over K. Now we want to apply the subspace theorem to product for me or S product for I from 1 to D of L nu I of Pn nu to this double product. And in order to do this, we have to estimate two things. First, the values of phi nu I of Pn, and then the height of the point phi 1 of Pn, phi d of Pn. Now for nu in in a second, so when the target point P nu is not at infinity, I claim that phi nu I of Pn as Noatic absolute value is uniformly bounded independently on n. This is because Pn tends to a point P nu, and the phi nu I at P nu is regular, not infinity. So this value tends to this value, which is a finite value. So the interesting case is what happens for nu in S prime. Then we take a local parameter T nu at P nu. So T nu is a regular function in a neighborhood of P nu with a simple zero at P nu. So when Pn tends to P nu, those functions having a pole at p nu will tend to infinity and the others will tend to 0. And more precisely, since phi nu I of Pn, this will be bounded by what? By T nu of Pn to minus the order of pole, which is minus n plus I minus 1, I think. So, yes. Okay. So the product so for nu in S prime, the product from 1 to d of the L nu I of Pn, which is the same thing, is bounded by T nu of Pn to the sum of these indices, which is d minus 1 over 2, because I make the sum not of I but of I minus 1, and minus d times n. Yes, which can be written as to d over 2 d minus 2n minus 1. So the main point you'll see in a moment is that d is at least 3n plus constant, because d is what comes from the Riemann-Roch theorem, which is n times the number of infinity, which is r, plus a big O of n. And so this exponent is positive, so I have a 0, not infinity. So the crucial product to estimate is this one for nu in S prime, and it has a big 0. For nu outside S prime, so in S second, I said that this is a big O1. So the total product for all nu in S of is less than the product for nu in S prime of this T nu Pn, and then I can erase to this exponent. Pardon? Ah, yes, yes, thank you. Okay, Bert. Yes. Well. Okay. Ah, yes, yes. Here it's no. certain. Here it was correct because I've already summed the exponent, of course. And now the height. So to estimate the height of one of Pn, d of Pn, which first of all, since there was some confusion last time whether it was had to add 1 or not, here it's basically the same. Because it's clear that constant 1 function belongs to this space. So we can suppose from the beginning that one of these functions is the constant 1 if you want. Otherwise, the constant 1 will be a constant coefficient linear combination of phi 1, phi d. So up to big O 1 is the same. So to calculate this, we have to estimate for each nu the maximum of phi 1 Pn nu and so on. So for nu not in S, we have that each of these functions takes a new integral value, so this is at most 1, because phi I of Pn is an S integer, as we said starting already at the beginning. So S integers means precisely that outside S its absolute value is at most 1. Now for nu in S but not in S prime, so for nu in S second, as before, I said that phi I of Pn nuadically is a big O of 1. And here I have just finitely many nu, so I can make a product of finitely many constants, obtain a constant. And the only problem is for nu in S prime. So some of these functions will be big because of the pole, and each one has a pole of order at most n, and at least one will have a pole of order n. So this maximum will be of the order of magnitude of T nu Pn to the minus n. This means that the ratio tends to a non-zero constant. So in particular, it will be at most T nu Pn to the minus n. So finally the height will be at most the product for nu in S prime of T nu Pn nuadic absolute value to the minus n. So finally what I obtain here is that this is less than the height to the minus d over 2n multiplied by d minus 2n minus 1. And now I just need that big O of 1, so it's at least 3 times n plus big O of 1. So I just need to choose n such that well, so d minus 2n minus 1 is larger than n plus go to the big O of 1. So I just need to choose n such that this is strictly positive. And so the theorem is proved, and so the subspace theorem can be applied. It's not yet finished because what's the conclusion of the subspace theorem? The conclusion is not that this inequality is impossible, is that its solutions lie in finitely many hyperplanes. This means that there are finitely many linear equations between phi 1, phi d, which are satisfied for our points. So there are linear equations of the form a1 phi 1 plus a d phi d equals 0, which are satisfied whenever I calculate this function on the sequence Pn. But every such functions, if a1, ad are not all 0, is non-zero, since the function phi 1, phi d are linearly independent. So each such function has only finitely many zeros on the curve. So it cannot be that the sequence Pn is infinite. Okay, so this. Yes. This is, I can consider this as a function.
So you're evaluating at phi 1, p1, p2, pn, right? What happens if pn's are going to infinity, but phi 1, pn is finitely many values?
No. Well, phi 1 can have can be constant, for instance. So it may be that phi 1 of Pn has only one value, but here I need that a certain regular function on the curve, which is not identically 0 on the curve. So this is not 0 on the curve, but it is 0 in Pn for infinitely many n. But a non-zero function cannot have infinitely many 0 on a curve. But this cannot happen. This can at most one of these functions can be constant. Okay. So so I've proved this particular case with 3 points, with at least 3 points at infinity. As I said, this is the crucial case because the general case can be deduced by this one using the so-called Chevalley-Weil theorem. It says the following. suppose we have two fine curves, C1 and C2. And we have, let's call it phi. It's an unramified cover. And all defined over a number field K. So there exists a number field K prime containing K such that every pardon?
You did not suppose everything went inside the affine piece. Then
Yes. Then yes. Then the height will be bounded, and so the sequence will also be very much. Yes. Yes. So the pre-image P consists of K prime rational points. And moreover, integral over well, not over S, so will be S prime integral. Well, S prime extends, so it's the set of places extending to in S. So basically S integral points here provide S integral points here up to enlarging the field of rationality and the ring of S integers. And using this trick, one can reduce, in the case C2 as positive genus, to having at least 3 points at infinity, because if you take so consider to be in the worst case with just 1 point at infinity, but with positive genus. So you see tilde as genus strictly positive, and tildes minus C as just 1 point. So there exists a cover of C which is not only unramified, of degree, for instance, 3, or more than 3, but also that it extends to unramified cover of the completion, which is still unramified. This is a consequence of having strictly positive genus. So even the complete curve is not simply connected, it has unramified covers of arbitrary degree, for instance, of degree 3. So in this case, over the unique point at infinity of C, which is the unique point of C tilde minus C, lie 3 points in C prime tilde. So the finiteness of integral points of C prime gives the finiteness of integral points on C. And on C prime we can apply our theorem. Okay, so I will maybe I will prove Chevalier-Weil theorem next time. So I think that finally in this course I will spend more time on curves than on surfaces, but by the way I've been told that you're more expert on curves than on surfaces, so perhaps you prefer. Concerning this proof of Siegel theorem, this is the proof that I found in a work in collaboration with Umberto Zanner. So the details can be found in a joint work with Umberto Zanner. Myself, it's published in Compte Rendu. The classical proof by Siegel used the embedding of the curve in its abelian variety, and in this series of lectures I'd like to avoid completely any recourse to abelian varieties. There are other proofs. First of all, via this argument, one can reduce Siegel theorem in all cases to a particular case of faulting theorem, even Siegel theorem for curves of genus 0 or 1, where Falting's finiteness theorem does not apply directly, can be deduced from Falting theorem after taking an unramified cover which can have higher genus. So the Falting's proof of the theorem in particular gives another proof of Siegel theorem. Another proof was provided by Carlo Gasbarri here. And finally, a completely different proof was given, but only it seems that it works only for P1 minus 3 points and for elliptic curves, and only over Q for the moment. It's been given by Mignon Kim, and it's a complicated proof, and it makes no use of this kind of Diophantine approximation. It's really different. Now can Baker, yes, but I think Baker only works for hyperelliptic curves. Yes, but yes, Baker's method, when it works, is effective. Well, none of this method is neither Siegel's nor the subspace theorem method nor the others I mentioned. Now some words on Chevalier-Weil theorem. As I said, proof will not be given today, but just show you some examples to convince you that it's a very reasonable theorem. So start with the case where C is Gm. So if you want C tilde is P1, and C can be viewed as P1 minus 0 infinity. So the unramified covers of Gm are always given by Gm itself with an isogeny, so up to covering automorphism are given by map for x to the n for some n. Now integral points on Gm, we already said just as so units. So what Chevalier-Weil theorem says that there exists a number field containing all nth roots of S units. And this is a consequence of the fact that the group of S units is finitely generated. So you have just to take the nth roots of the generators. You have a finite number of roots, so a finite number of algebraic numbers. They define a field of finite degree over Q. So there exists a finite extension of the ground field containing all nth roots. So consider an example examples in the compact case. So C equals C tilde, so it is already C itself is compact, and in this case I recall that integral points are just rational points. So in this case the theorem applies to all k rational points. So examples, I cannot take for C P1 because P1 is simply connected, it has no non-trivial unramified covers. So the first interesting example is provided by elliptic curves. So take E and an elliptic curve and consider the unramified cover of E given by E itself. For instance, the multiplication by two maps. So multiplication by 2 with respect to the group law on the elliptic curve. Then it is a consequence of Mordell-Weil finite generation theorem. you have that the group rational point modulo the subgroup of multiple of 2 is finite. So again, every point in a K is of the form, every point P in K is of the form P equals twice P prime plus R, where P prime is again rational and R has finitely many possibilities. So if you want to divide by 2P, you have just to divide by 2R, this finite set of representatives, and so you obtain that every point P is the sum of a rational point plus a point in a finite set, and there will be a finite extension of the ground field containing the coordinates of all these R over 2, the square roots in this sense of the points R. So over finite extension of the field of rationality, you can say that every point becomes of the form 2P. So again, every rational point has a rational pre-image in this larger field. Now, actually, we need Chevalier-Weil theorem only in particular cases. In each case, we just need to work over a particular unramified cover of degree larger than 1. We don't need to consider all covers, and perhaps it's better to restrict to abelian covers, so covers which are Galois within abelian Galois groups, and they reduce to cyclic covers because every abelian group is a product of finite cyclic groups. So we have just to consider cover of this form, which are Galois with a cyclic group. Now, if we think at extensions of function fields, we have the function fields of C2, which embeds into the function fields of C1. And the fact that it is Galois with cyclic group, at least in the case which we can suppose is our case, where K contains sufficiently many roots of unity, means exactly that K of C1 has been obtained from the field K of C2 by adding the nth root of a rational function f. F is K of C2 is a rational function. So by Kummer theory, all cyclic extensions of a field which contains all nth roots of unity are obtained by extracting nth roots of unity. And the fact that this cover is unramified means exactly the following fact, that F is locally a nth power and everywhere. So for every, you can work with the complex topology to simplify. For every point on the curve, locally in the complex topology, F is an nth power in the ring of power series, or if you want, a holomorphic or meromorphic function in a neighborhood of this point. And this means that all zeros and poles of F have order divisible by n. This is the only local obstruction to extracting an nth root of a holomorphic function. So if a function in one point is regular and non-zero, you can extract the square root in two different ways. If it has a simple zero, certainly it's not a square locally, because its square root would have a zero of order 1/2, and it's not possible. But if it has a double zero, then locally it's a z square multiplied by a function with no zero, and you can again take square root. So the only obstruction is of this kind. And the arithmetic significance of Chevalier-Weil theorem is that if F is locally everywhere in the sense of the complex topology a nth power, its values at integral points will be almost nth power, which means nth powers multiplied by a finite number of elements of this kind, which are not perfect nth power. So up to extracting the nth root of some bad terms which are not nth power, you obtain a finite extension of the ground field where F takes such that at each integral point on C2, F takes values which are perfect powers. So the geometric condition of being nth power locally everywhere implies the arithmetic condition of taking values which are basically nth power. And you can say, you can see this fact in a particular case of an elliptic curve. Consider the elliptic curve, for instance, y square equals x3 plus 3, x for instance. For the coordinates is this one. So the function, as I prefer to write small x for capital X over Z and small y for capital Y over Z. Now the function x is locally a square everywhere. Okay, this is because so here I should have written with small letters. Because here we write x multiplied by x squared plus 3, whenever x vanishes, the second term does not vanish, but the product is a square. Since this term does not vanish, the 0 of the product is the 0 of x, which means that the 0 of x has order even. Actually, it has order 2. And the same for the poles. For the poles, we have, whenever x has a poles, x squared plus 3 has a poles of order twice the 1 of x. So the right-hand term has a pole of order 3 times the order of x. And if 3 times a number is an even number, that this number is an even number. So, so the pole of x has, well, x has a pole of even order. Actually, it has a pole of order 2. So, so it's a square locally everywhere. And now it is easy to see that if you take a rational point, so if x, y is a rational point, so we can write with a common denominator a over d and b over d. We have a square over d square equals, no, it's b square. It's a 3 plus 3 times b over d, so it's, which is a plus 3b d square. So you see it's something 3a over d. Okay. So now, for instance, if AD and BD are coprimes, which is not always the case, then this function, this fraction is reduced. This fraction is reduced. This here the denominator is a square, which means that d cube also must be a square. So d must be a square. So we already proved that the denominator of x is a square, and then the same here we have a multiplied by a square plus 3 d square. So if a prime divides a and does not divide d, then it does not divide a square plus 3d square. So the multiplicity in which appears in the denominator is multiplicity in which appears in a, and this must be a square. Of course, we have to take to account the case in which a, d, or b over d are not coprime, and you see that up to a finite number of possible primes, x will be a square. So I stop here.